In the last few weeks, you have learned about electron configurations, both how to write them and which electron configurations represent chemically stable situations. You've learned how to draw Lewis structures for atoms and molecules, and how to use average valence electron energy and electronegativity to know how well an atom holds on to its electrons. We can put all these thoughts together to answer the question, why bond? The easy answer is to be isoelectronic with the noble gases. But we can now understand some of the more subtle features of bond formation. Let's start by considering magnesium and chlorine. If magnesium wants to become isoelectronic with a noble gas, it really has two choices. It can lose 2 electrons to become isoelectronic with neon, or it can gain 6 electrons to become isoelectronic with argon. As we look at the two possibilities, our first thought is to say that it would be easier for magnesium to lose 2 electrons than gain 6, simply because 2 is a smaller number than 6. But chemically, there are some reasons why magnesium will lose 2 electrons rather than gain 6 electrons when forming a bond. The first reason is the average valence electron energy. Magnesium has a relatively small average valence electron energy, which means that it doesn't hold on to its valence electrons very tightly, and therefore it can lose its valence electrons relatively easily. Likewise, magnesium also has a relatively small electronegativity. That small electronegativity means that magnesium lacks the ability to draw 6 new electrons to itself. So magnesium, in forming chemical bonds, is going to lose 2 electrons. Chlorine, in becoming isoelectronic with a noble gas, has the option of losing 7 electrons to become isoelectronic with neon, or gaining 1 electron to become isoelectronic with argon. Again, we look at the situation and we feel like gaining 1 electron would sure be a lot easier than losing 7 electrons. But we have to remember the chemistry behind this. Chlorine has a relatively large average valence electron energy. That means it holds on to its valence electrons quite tightly. That being the case, chlorine isn't going to be able to lose 7 valence electrons. It also has a relatively large electronegativity. That large electronegativity enables chlorine to not only hang on to its own valence electrons, but to attract the valence electrons of other atoms to itself. Looking at this situation, we appear to have a match made in heaven. Magnesium would like to lose electrons, chlorine would like to gain electrons, and the formation of a chemical compound is relatively easy. Magnesium will lose 2 electrons to form a magnesium 2 positive ion, and 2 chlorine atoms will each gain 1 electron to form 2 chloride ions. The final result here is that we form magnesium chloride, MgCl2, via an ionic bond, which is a situation where electrons are transferred from an element with a small electronegativity to an element with a relatively large electronegativity. In the end, all of the elements end up being isoelectronic with one of the noble gases. Now let's consider another situation. Let's consider the situation involving nitrogen and fluorine. To become isoelectronic with a noble gas, Nitrogen can either lose 5 electrons or gain 3 electrons. Again, we look at the situation and feel like gaining 3 electrons is probably the easier possibility. Considering what we know about average valence electron energy and electronegativity, we realize that this will probably work out. Nitrogen has a relatively large average valence electron energy, meaning that it can't really lose 5 valence electrons, but it has a large electronegativity, which means that it stands a pretty good chance of attracting 3 valence electrons from someplace else. Giving the same consideration to fluorine, to become isoelectronic with a noble gas, fluorine can either lose 7 electrons or gain 1 electron. Gaining 1 electron certainly seems like an easier task, and this is supported by fluorine's large average valence electron energy, saying that it does not want to lose 7 electrons, and by its extremely large electronegativity, saying that fluorine is more than capable of attracting valence electrons from other atoms. This time it doesn't look like we have a match made in heaven. We have a situation where both elements want to gain electrons and neither element wants to lose electrons. The only way this is going to work out is if the elements share their valence electrons. We have encountered this when drawing Lewis structures, and we're relatively comfortable with organizing the elements in such a way that one nitrogen atom shares 1 valence electron with each of 3 fluorine atoms, and each of those 3 fluorine atoms shares 1 valence electron with the nitrogen atom to create a molecule where all of the elements have access to 8 valence electrons. This creates the chemical compound NF3, and the bonds present in NF3 are covalent bonds, or bonds formed by the sharing of valence electrons. Through this sharing, a situation has been created where all of the elements in the molecule now have electron configurations that are isoelectronic with the noble gases. So looking at what we know about average valence electron energy, electronegativity, and an element's desire to become isoelectronic with a noble gas, we've considered 2 possible ways that bonds can be formed: through the sharing of valence electrons, as in NF3, and through the transfer of valence electrons, as we had in the situation with the MgCl2.